Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 6, Lesson 6 on Solutions to Inequalities. Inequalities? Wait, what? So throughout this entire unit we've been working with equations, all right? And we've talked about how equations are true and false, or open. We've looked at how to solve equations, finding the values of the variables that make them true. But now today we talk about inequalities. And the big difference between inequalities and equalities is that inequalities are comparing whether numbers are greater than or less than other numbers, right? But everything else is basically the same as with equations. In other words, it's all really about whether or not values of variables make the inequality true or whether it makes them false. So let's start off with that idea of true-false comparisons. Let's get to it right in exercise number 1. Inequalities are a lot like equations. They can be true, false, or open. Let's take a look at exercise number 1. State whether each of the following inequalities are true or false. All right. Now, of course, there are some inequalities that are exceptionally easy to tell whether they're true or false. 8 is greater than 3. Yes, 8 is greater than 3, so I'm going to say true, right? That one's an easy inequality to judge. As soon as we have mathematical expressions or fractions or whatever, on both sides, then we might have to do a little bit of work, right? So for instance, in letter B, is 10 minus 3 less than 9? Well, 10 minus 3 is equal to 7. Is 7 less than 9? The answer is yeah, so that's true, right? Letter C, is 17 halves less than 9 1/4? Now that's a little bit trickier, right? How would we go about comparing those? Well, there's a couple different ways. We could convert the 9 1/4 to an improper fraction, but it's going to have denominators of fourths, and then we could change this one to have denominators of fourths. And then we could compare, how many fourths are on both sides. I kind of like the idea of actually taking 17 halves and converting it into a mixed number. So pause the video right now, convert 17 halves into a mixed number, rewrite the inequality like that, and then judge whether it's true or false. Take a moment for this. All right, well, 17 halves is the same as 8 1/2. And is 8 1/2 less than 9 1/4? Absolutely. Apparently, I really liked these to be true this time. Wouldn't have been hard to make one false. I could just reverse the inequality symbol pretty much on any one of these and it would suddenly turn to be false. Now, letter D is a very important one. Is 5 squared greater than 25? Well, 5 squared, or 5 to the second power, is 5 times 5. And as we all should know, 5 times 5 is 25. Watch out, it's not 10, right? So the question is 25 greater than 25? And I hope the answer would be no, right? A number is only greater than another number if it lies to the right of it on the number line. And the plain fact is 25 doesn't lie to the right of itself on a number line, it lies right in the same place as it on the number line. So 25 is not greater than 25. That's false. And that's actually a very important case. There's often a situation where you get something like 6 is less than 6 or 7 is greater than 7. And those are all false inequalities. A number cannot be greater than itself. A number cannot be less than itself. Let's keep moving on with these. Let's introduce kind of maybe a new idea. See, sometimes inequalities actually include the equality. The way you do that is you take either the greater than symbol or the less than symbol and you put a little line underneath it. And that line underneath it then means that the equality is there as well. So this symbol, this greater than with a little line underneath it, represents greater than or equal to. So what you're really asking in that question is, are the two numbers on either side of that symbol, is the number greater than the other number, or is it equal to the other number, right? The only way this one's going to be false is if the number on the left is smaller than the number on the right. And the same thing goes for this symbol. This is the less than or equal to symbol. It's going to be true if the number on the left is either less than or equal to the number on the right. So let's take a look at this. Exercise number 2. State whether each of the following inequalities is true or false. All right. Well, if this said 11 is greater than 11, we would say false, totally false. But this actually says 11 is greater than or equal to 11, and that's true. And it's true because 11 is equal to 11. Now, if the logic here is somewhat confusing to you, let me put it in terms of not numbers, but how about me? If I walked up to you and I said, hey, I'm either a math teacher or an NBA basketball player, right? Would you say that I was telling the truth or lying, right? And the answer is I'm telling the truth because I'm a math teacher. I'm not an NBA basketball player, but that's irrelevant, right? I'm just asking, am I if I said to you, I'm either a math teacher or an NBA basketball player, am I telling you the truth? You'd say, yeah, because you're a math teacher, right? Now, on the other hand, if I said, I am either a doctor or an NBA basketball player, you'd say, well, that's a lie, because you're not either one of those things, okay? So that's the way we want to kind of think about these. So taking a look at letter B, right? Letter B says 16 is less than or equal to 40 halves. And again, this is a little bit tricky, but as long as we can evaluate the 40 divided by 2 and we get 20, right, then we can say, well, is 16 less than or equal to 20? And the answer is yes. Yeah, that's true, because 16 is less than 20, right? One of the two things has to be true. Either the equality has to be true or the inequality has to be true. Now, of course, these are going to get a little more complicated. What I'd like you to do is pause the video, evaluate both expressions, right, keeping that inequality sign going on both of these things, and evaluate whether the statements are true or false. Pause the video now and take a few minutes. All right, let me just kind of divide this up so we've got a little bit of room. Here, I'm going to have 2 times 4, which is 8, is less than or equal to 10 minus 3, which is 7. Well, is 8 less than or equal to 7? Well, 8 is not less than 7, and 8 is not equal to 7. Since both of those are not true, the answer is false. All right. Now letter D. This one's going to take a little bit more work. On the left-hand side, we have 6 to the second power, or 6 squared. So 6 times 6 is 36, greater than or equal to 2 times, well, 11 plus 7 is 18. Now I have to figure that one out. 2 times 18 is 36. So now I look at that and I say, well, is 36 greater than 36? Definitely not. Is 36 equal to 36? Yes. So that's true. All right. It's got to be one of them. It's either got to be greater than or equal to. Can't be greater than and equal to. That's impossible. All right. But it's got to be either greater than or equal to in this case, and since it's equal to, the answer is true. All right, so judging the true-false nature of inequalities, even if they have the equality symbol in them, is actually pretty easy. All right. Let's now take a look at solutions to inequalities, because that's a little different than solutions to equations. Now, don't get me wrong, solutions to inequalities are still just the values of the variables that make the inequality true. And that should sound familiar. You know, I have a like, sound familiar question mark, right? Because that's just what a solution to an equation is, right? It's any value that makes it true. Same thing with solutions to inequalities. So let's take a look at exercise number 3. State whether each of the following values is a solution to the inequality. Show the work that leads to your conclusion. All right, this is absolutely no different than what we've been doing in every single lesson when we've seen whether or not a value was a solution to an equation. I want to see, is 7 a solution to this inequality? So what I'm going to do is I'm going to take 7, I'm going to substitute it in for x, I'm going to get 7 plus 9 is greater than 14. 7 plus 9 is 16. Is 16 greater than 14? Yes, that's true. Therefore, the answer is yes, 7 is a solution to this inequality. All right, very, very simple. I'd like you to pause the video now and see if c equals 5 is a solution to this inequality and y equals 4 is a solution to that one. Pause the video now and take a little bit of time. All right, let's take a look. All right, in letter B, we have 4 times c is less than or equal to 20. Let me put in 5 for c. All right, 4 times 5 is 20. Is 20 less than or equal to 20? Yes, it certainly is because it's equal to 20. And therefore, yes, this is a solution to the inequality. All right. And finally, letter C, right? I want to take y equals 4 and I want to substitute it into the equation. That's simple enough. Let me take that, plug it in. We're going to get 2 times 4 plus 7 is greater than or equal to 22. 2 times 4 is 8. So now 8 plus 7 is greater than or equal to 22. 8 plus 7 is 15. Is 15 greater than or equal to 22? The answer is most certainly no. False. So this is not a solution to the inequality. All right, so again, judging whether or not a particular number is or isn't a solution to an inequality is very easy. What we're going to look at next is actually a bit more confusing, which is how we can show all the values that solve very, very simple inequalities, all right? Because if you haven't noticed so far, every equation that we've solved so far has had only one solution. But there are often an infinite number of solutions, meaning we can't even count them, right? There are so many. There can be an infinite number of solutions to inequalities. The question is, how can we visualize those? All right, so let's take a look at exercise number 4. Let me bring it all the way up to the top. I already kind of talked about what was up there. Exercise number 4. Consider the very simple inequality x is greater than or equal to 3. Letter A, in the table below are various values of x that correspond to points on the number line. Put a y if the value of x is a solution, and put n if the value of x is not a solution to the inequality, that is. All right, so let's talk about this a little bit. I just grabbed a bunch of random values of x, okay? Obviously, this number line has an infinite values of x, not just 10 or 11 or whatever, you know, because there's all these decimals and fractions and things like that in there, right? But we've just got this really simple inequality. X is greater than or equal to 3. So for instance, if x was 1, right? If x was 1 and I put it in here, 1 is greater than or equal to 3? No, that's not a solution, right? If I took x equals 2 and I substituted it into the inequality, 2 is greater than or equal to 3. No, 2 is definitely not greater than and certainly not equal to 3. Now we get to ones that are a little bit harder. 3. If I put x equals 3 in here, is 3 greater than or equal to 3? Well, yeah. You know, it's not greater than itself, but it's certainly equal to 3. So this is my first one, and I guess I was supposed to be putting y and n according to the directions. Apparently I just don't read my own directions very well. But yeah, that one's the solution, right? 3.5, well, if I put 3.5 up here, 3.5 greater than or equal to 3? Sure, it's not equal to 3, but it's greater than 3. So that's a yes. You know, x equals 5. 5 is greater than or equal to 3? Yeah, 5 is greater than or equal to 3. That's yes. 0.5, right? 1/2, same thing as 1/2, right? 0.5, is 0.5 greater than or equal to 3? Oh no, 0.5 is most certainly much smaller than 3. Well, maybe not much smaller, but it's definitely smaller than it. And finally, x equals 9. Is 9 greater than or equal to 3? Yeah, of course it is. 9's certainly greater than or equal to 3. So, take a look. Just in this table alone, we have 1, 2, 3, 4 solutions to this inequality. But of course, there's lots of solutions to this inequality, and just common sense-wise, right? Every solution to this inequality will be any number that is either greater than 3 or equal to 3. And let's take a look at what that looks like on a number line. Letter B, right? Plot and label each point on the number line and circle it if it's a solution, right? So I'm going to plot every single one of these numbers on the number line, then I'm going to circle it if it's a solution, I'm not going to circle it if it's not. So for instance, x equals 1, that's simple enough, right? That's right here, I'll label an A up here, but I'm not going to circle it because it's not a solution. B is right here, but I'm not going to circle it because it's not a solution. C is right here, I am going to circle it, that was a solution. 3.5, I'm going to have to wing that one a little bit, it's right here, that was a solution. 5 was right here, that was letter E, or point E, that I'm going to circle, it was a solution. 0.5, letter F, is way down here, but I'm not going to solve that, or I'm not going to circle it. And then 9, which is way out here, I'm going to circle that and it's there. All right, now, to take a look at this for a second, I'm going to write down the number 3 right here, because that's where we are. Take a look, right? The inequality was x is greater than or equal to 3. Everything that I circled was either a number that was equal to 3 or a number that lied to the right of 3. And that should make sense, right? We should know that a number is greater than another number if it lies to the right of it. So when we look at x is greater than or equal to 3, we should really think to ourselves, oh, the solution to that inequality is going to include the number 3 and then every number to the right of 3. Because any number to the right of 3 is going to be greater than it. And that gets into letter C, right? Let's take a look. A solution set of an inequality or equation is all the values that solve the inequality or the equation. Shade the solution set to x is greater than or equal to 3 on the number line above. Now, I mean, think about this for a moment, right? If I was going to actually try to plot all the different numbers that solve this inequality, I would be, you know, that number, that number, that number, that number, that number, this number, right? All those numbers, no matter what they are, would be greater than 3. This is the only number that's equal to 3. And I wouldn't have anything over here, right? So how do I shade the number line? The way that you do that is I'm going to get rid of this circle right now, all right? But I literally draw a nice big point at 3, because 3 is included, and then I just draw over the number line, really nice and like heavy, and then I put an arrow at the end indicating that any other number that's to the right is still going to be part of my solution set. What some students like doing, and there's nothing wrong with this, is kind of doing this above or below the number line, because it can get kind of messy on the number line. What I mean by that is that you could very easily, let me just move that 3 up a bit, you could very easily have just put a big filled in dot here and then drawn kind of an arrow like that to indicate that every number, right, every number from 3 going to the right is going to be a solution to x is greater than or equal to 3. All right, let's look at one last case which is a bit trickier. All right, plotting the solution set when the equality is not included can be confusing. So the last inequality was x greater than or equal to 3. Now I'd like to think about the inequality x is less than 7. Let's take a look at letter A. Would x equal 7 be a solution to this inequality? Why or why not? Well, pause the video now and see if you can answer that question. Would 7 be a solution to the inequality x is less than 7? Well, and the answer is no, right? And I can test it, right? I can test it like I can test any other value, right? I could actually put the 7, if I can actually draw an arrow, I could put the 7 into the inequality. I would find that that's false. 7 is not less than itself. So the answer is a big fat no. So before we even go on to the rest of this problem, if I were to now kind of do that arrow business with, shading and whatnot, I better not have 7 shaded. I better not indicate that 7 is part of the inequality. But here's where it gets a little confusing. Take a look at letter B. Would x equals 6.99 be a solution to the inequality? How close would this be to the number x equals 7 on the number line? And would it be to the right or the left? All right, so this was a threefer. I asked 3 questions for this entire question. So first thing, would 6.99 be a solution to the inequality? Think about that. Well, the answer is yes. And again, just like before, I could take 6.99, substitute it into the inequality, and the question is 6.99 less than 7? That's true, so the answer is yes. Now, why do I pick 6.99? I picked 6.99 because of the second question. How close would this be to x equals 7 on the number line? Very close. I mean, so close, right? So close. Let me come down to the number line for a second. Here's 7. Here's 6. 6.99 would be, I mean, it'd be like maybe right there, maybe even a little bit closer. That might be like where 6.9 is. But let me pretend it was 6.99. I mean, it'd be close. And that answers the third question, to the right or the left. Well, it'd be to the left of it, right? Now, keep in mind, right, 7 is not part of the solution to this inequality. Let me write the inequality right here so I don't have to go back up, right? 7 is not part of the inequality, but 6.99 is. By the way, so is 6, because 6 is less than 7. So is 5. 5 is less than 7. So is 2.5, right? That would be right here. It's less than 7. In fact, any number to the left of 7 is going to be less than it. So how do I show the fact that all the numbers to the left of 7, even a number really, 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 really close to 7, right? How do I show that every number left of 7 is in the solution, but just not 7 itself? And that's where students can get very confused, because the way you do it, and this is letter C, is you draw an open circle around 7, okay, indicating that you have not colored it in. Isn't that kind of weird? Like, so you have a nice heavy dot there. This is the last problem, right? Whoops, oh, that's 2 problems ago. You put a nice heavy dot. If the number, right, the 3 is included. Remember, this was x is greater than or equal to 3. So I fill in that dot on 3 because 3 is included. On the other hand, right, 7 is not included, but everything to the left of 7 is, because I want all the numbers that are less than 7. And that is literally all the numbers down here. Now again, if you don't really like the shading on the number line, if that's kind of annoying to you, you could always do the open circle either above or below the 7, and then do the arrow to the left. But the key is, if the number is included, that should be a filled-in circle if there's an equality there. And if there isn't an equality there, if it's strictly a less than or greater than, then you should have a nice open circle to indicate that, oh yeah, every number up to 7, but not 7 itself. All right, and that includes numbers very close to 7, like 6.99 or 6.99999, right? Those numbers are all very, very close to 7, but still to the left of it. All right, let's wrap this thing up. Inequalities are very, very similar to equations. All right, the biggest difference is that they tend to have a lot more solutions than equations do. In fact, many times, most of the times, they have an infinite number of solutions. But to see if a value of x, or whatever variable we're talking about, is a solution to an inequality, we simply substitute it back in like we would with an equation. Plotting all the solutions to an inequality can be tricky, especially when the inequality doesn't have the equal sign kind of tacked on. When it does have the equal sign tacked on, we fill in the dot and then we shade either to the left or to the right, depending on whether or not it's a greater than or a less than. And if the equality is not included, we put a nice open circle above the number, and again, either shade to the right or shade to the left, depending on whether it's greater than or less than. We've got one more lesson on inequalities, so we'll get a little bit more work with that shading. Get some work with it on the homework. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.